At Cheenta, we are trying to inculcate several experimental temper in children from any age, and kids should learn and from play with the science and innovate. So keeping that in mind, we, along with the problem solving techniques, we are kind of bringing experimental form of that is, which is the integral part of our programs. I am Tanumay Banerjee. I am a physics faculty at Cheenta. So today we have Panchajan Day. Today we'll be taking very interesting problem from INPhO level. Okay, so Panchajan, can you please present the problem? We can just discuss about how to strategize for such problems, such level of problems, so that what approach can we build up to solve these kind of problems. All right.
So this problem is from INPhO 2023. This problem is about a ball that is thrown from the surface such that it almost touches the ceiling, and then it comes back without hitting. And then the ball hits the floor several times, and we are using some app called Wave Editor, which records the sound signal produced from the ball when it hits the surface. And this is the recording of the audio signal. Now, from the audio signal, we will try to find what is the height of the classroom. So we will try to find the height of the classroom from this data. These times are mentioned in seconds. So these peaks correspond to every time the ball hit the surface. And now from that, we will try to find what is the height of the classroom. This is the first hit.
Okay, so before we start with the problem, I would like to ask you that what kind of strategy we can approach for solving these kind of problems, like how these INPhO problems are different from other examination like JEE and all that we give.
With theoretical understanding, you can do projectile motion and stuff like that, but you also have to build a experimental understanding so that when you are given an experimental problem like this, some result of some recording, you have to retrieve the data from your experimental setup.
Okay.
So you also need some experimental knowledge about the setup.
Okay, yeah. So at Cheenta, we are already dealing with such problems from very basic to advanced level. In the basics level, we have AlgoDo, and in advanced level, we can use different data sets from different simulations applications that are already available there.
We do simulations via AlgoDo, and student can actually see or visualize the problem, and that would help a lot, because once you can visualize a problem, it's very easy to build an understanding and to solve various scenarios of the same problem.
Yeah.
So it's very important to have an experimental understanding.
Are we using any simulation to explain this one?
No. This is just the data is given. We'll just retrieve the information from the data.
So you can show the free body diagram, like how the problem.
Yes, sure. So in this problem, suppose this is our ceiling and this is the floor. Now what is mentioned is that when the ball was thrown, it almost touches the ceiling. So suppose the ball touches the ceiling here, almost touches the ceiling here, and now it starts falling from there. And suppose it took some time t1 to fall, and then it jumps again. But suppose for a general scenario, let's say the ball doesn't jump at the same height, but it may also jump. We'll consider a coefficient of restitution E. Coefficient of restitution. First, what is the free body diagram of the ball?
Okay, can you
consider the ball?
Detail on what is coefficient of restitution?
Yes, coefficient of restitution is the ratio of velocity of separation by velocity of approach. That means, suppose there is a surface here and I throw a ball and the ball have initial velocity v. So this is our velocity of approach. And after collision, suppose the ball comes back with a velocity v prime. So this is our velocity of separation.
Okay.
Then our E will be v prime by v. Now, our ball have a free body diagram like this. There is only one external force acting on the ball, and that is mg. At the time of collision, there will be an impulsive normal force by the floor or the ceiling. In this case, it will be only due to the floor because the ceiling just touches the ball. So there will be no impulsive normal due to the ceiling. But in these points, there will be impulsive normal force that just changes the direction of motion of the ball. Now, since the acceleration of the ball throughout the fall is g, we can say that if max height of ball is h, then time taken to fall on ground, that will be, let's say it's t, then we can write half g t square, not half g t by 2. Why I'm writing t by 2? Because it's taking t by 2 time to reach the top and then t by 2 time to reach again the surface. And this is, suppose I say h, this is our h. Then this will be our h. Half g t by 2 square is h. And that gives us a relation that h equal to g t square by 8. Now, since for different jumps, now let's see the data. So jump number versus time. First jump, it's at 10 seconds, 10.26 seconds. Second jump, it is 11.409. Third jump is 12.244. Fourth jump is 12.848. Now, as you can see, this is the total time. So
for this data is coming from the already given, right?
Yeah.
Okay.
But we need to find the time interval, not the total time.
Yeah.
So we'll take the time intervals. And for the first jump, we don't know what is exactly the time interval because the recording of the app might have started before even the ball was thrown or even after the ball was thrown. So we cannot mention anything for the first jump. But for the second jump, the time interval is this minus this. And that we can write as 9, 4. This 4 minus 2 is 2. So 1.149 seconds. Similarly, the time interval for the third jump, if you see, it's 44 minus 9, that is 35. 2 minus 4, 8, 0.835. And for the fourth jump, it is 0.604. So you can see that the jump time is decreasing. This time interval, if I say this is T1 and if I say this is T2, then the time interval is constantly decreasing. That means our coefficient of restitution is less than 1. Why? For coefficient of restitution equal to 1 scenario, our velocity of approach will be velocity of
equal to
separation. That means that the ball would hit the surface. If the ball hits the surface at some velocity v, it leaves the surface with the same velocity. And since we know that time of flight will be delta t equal to 2v by g, for a coefficient of restitution equal to 1 case, our time of flight for each successive interval will not change because the v doesn't change. But we are seeing that our time of flight is decreasing. What that implies? That implies that suppose this is v1 and suppose this is v2, then delta t1 greater than delta t2 implies 2v1 by g greater than 2v2 by g, which implies v1 greater than v2, which also implies 1 greater than v2 by v1, which was our definition of E, coefficient of restitution. So that means our coefficient of restitution for this experiment is less than 1.
Also, what can we like conclude about the elasticity of the surface here? Is there anything?
So what we can say is that our E is less than 1. That implies that our ball is constantly losing energy whenever it hits the surface. So some amount of the kinetic energy of the ball is going in the form of sound energy and thermal energy. And that sound we are recording.
Correct.
Like that. Now, the time of flight of the ball, we can write delta t equal to 2v by g. Now, also observe a thing that for a successive time interval, the velocity will change like this: v from v to ev, then e square v, then e cube v, like that. After each collision, E is multiplied with the velocity of the ball because E is velocity of separation by velocity of approach. So then we can write velocity of separation equal to E times velocity of approach. In this case, velocity of approach was v, so velocity of separation is ev. But this ev will be our velocity of approach in the next collision. So that's why our velocity for each successive interval will follow a GP series. So in this time interval, our velocity, if it's v, then in the next interval it will be ve, then it will be v square, like that. Now from that we can also say, then since our velocities are in GP, our time intervals, which is given by 2v by g, that will also be in GP. Our time intervals will be like this: delta t1, comma, e times delta t1, comma, e squared delta t1. So our delta tn will be e power n minus 1 delta t1. This is the general time interval of nth collision. Now, there are two ways to solve after we obtain this relation. See, we have obtained delta t2. We have delta t3, delta t4. Now we can do two things. We know that they will be in GP. So we can simply write t1 times t3 will be t2 squared, which is a property of the GP. And we have t2, we have t3. From that we can calculate t1 equal to t2 squared by t3. And that gives us t1 equals to 1.149 squared by t3 is 0.835. Right? And this is in seconds. And then how do we calculate the height of the ceiling? To calculate the height of the ceiling, remember the fact that the first jump just touched the ceiling. So if this is the first jump, then this height is the height of the ceiling. And we can write h equal to half g t1 by 2 whole square. That gives us height of the ceiling as half g t2 to the power 4 t3 squared. I'm just substituting. And then we need to use a calculator to find the final expression. And let's see what it gives. So we'll put 1.149 to the power 4 by 0.835 square. This was in meter per second square, and this is second square. So our final answer will be in meters. So let's see, our answer will be, and if you calculate this, you will get 3.062 meter as your answer. Now, the method I just mentioned is one way to solve the problem. There is another way, but that needs plotting a graph. But we'll see that way as well, because that way is more accurate. See, you have been given delta T2, delta T3, delta T4. Even after that, you have fifth collision and sixth collision. There are total 1, 2, 3, 4, 5, 6, 7, 8 collisions given in the data. So if you write down all the delta T values, then you would have a data set which will have T2, T3, T4 up till delta T8. And you don't have delta T1. And you know that they are in GP. So you can write delta T2 as E times delta T1. And similarly, E to the power 7 times delta T8, T1. What you can do is that you plot a log graph. You can plot a graph of log Tn versus n. That would give us, suppose I take our expression of Tn was e to the power n minus 1 T1. So if I take log both sides, we'll get log Tn equal to n minus 1 log e. This e, don't confuse this e with a natural e, which is equal to 2.718. Don't confuse them, because this e is our coefficient of restitution. So this is not the e we want. Log delta T1. Now it's better to plot a graph of n minus 1 versus log delta Tn. Then this is our y coordinate, so I write it y. This is our x coordinate, I write it x. This is a slope kind of term, so I write it m. And this is our intercept, c. We get a y equal to mx plus c, a straight line. And we have some data sets. You fit a straight line, and you will see there will be an intercept, some intercept here. And that intercept c is log delta T1. So this is another way to find delta T1, and this is more accurate. Why? Because this time we are using the entire data set rather than relying on just these two data. So this is more accurate. If you do this approach as well, you will get similar answers, 3.06 meter. You find delta T1 from this approach, and then put it in the equation half g T1 by 2 square. That gives us height equal to 3.06 meters. So there are two approaches. One is just taking two values, T3 and T2, and calculating the time for the first collision, or the alternative approach is take all the data points, plot a graph, and that will help you to find the first collision time. And so in this way, we can solve this problem.
So thank you for explaining the methods, these two methods which we can approach and by which we can solve the problem like this. And this way we will continue to explain such kind of problems which will be helpful for students to understand that how to approach these questions and how to deal with this.